Press a button and a can turns liquid into mist. No pump, no motor, no power at all. Just a sealed steel cylinder that has been waiting, sometimes for years, to push its contents out in a perfect, even cloud. How does an aerosol spray can work? The answer is a gas trapped as a liquid and a pressure trick that never winds down. Today we slice the can open and watch the whole machine fire in slow motion. Cut the can open and you find two things sharing one space. At the bottom sits a pool of liquid. It is mostly the product: paint, deodorant, cooking oil, blended with something stranger, the propellant. Above the pool is a pocket of gas, pressing down on everything below. That gas pocket is the engine of the whole can. There is no pump hidden inside, no compressed spring. Just liquid below, pressure above, and a sealed steel wall holding the standoff. The propellant is the secret. At room temperature and normal pressure, it wants to be a gas. Something like propane or butane, or a compressed gas like nitrogen. But at the factory, it is forced into the can under pressure, several times higher than the air around you. Squeeze a gas hard enough and it gives up. It condenses into a liquid and settles into the pool. A gas in disguise, stored 100 times more densely than it could ever be as vapor. Now the can sits on a shelf, perfectly balanced. Some of the liquid propellant evaporates, filling the space above the pool with vapor. That vapor pushes back down on the liquid surface. When the push gets strong enough, evaporation stops. Scientists call this vapor pressure, and it is self-regulating. Too little gas above, and more liquid boils off to replace it. Too much, and vapor condenses back into the pool. The can holds itself at one exact pressure, automatically, for years. Look closer at the cutaway and you will see a thin plastic straw running from the valve at the top all the way down to the bottom of the can. This is the dip tube. Its job is simple but essential. It gives the liquid a path out while keeping the gas pocket sealed in. The pressure must push on the liquid, not escape past it. That is also why a can sprayed upside down just hisses gas. The tube's opening is suddenly sitting in vapor, not liquid. At the top of the can sits the only real machine in the whole device, the valve. It is a tiny assembly, smaller than a fingernail. A hollow stem passes up through a rubber gasket, and a small spring pushes the stem upward, holding a hole in its side pressed tight against that gasket. Sealed. As long as nothing pushes down, the gasket blocks the hole completely, and the pressurized contents have no way out. One spring, one gasket, one stem. That is the entire lock. Now your finger arrives. You push the button, and the button pushes the stem down against its spring, about 1 millimeter of travel. That tiny slide drags the hole in the stem's side down past the rubber gasket into the open chamber below. Suddenly the geometry changes. The hole that was sealed is now exposed to the inside of the can. A path exists, up the dip tube, through the valve body, into the hollow stem, and out toward your fingertip. The moment the path opens, the gas pocket goes to work. Remember, it has been pressing down on the liquid surface this whole time, at several times atmospheric pressure. Now there is somewhere for that force to go. The gas shoves the liquid down, and the only escape is the mouth of the dip tube. Liquid races up the straw, through the valve and into the stem. Not sucked from above, but pushed from behind, like squeezing the bottom of a toothpaste tube. The liquid arrives at the nozzle moving fast, and the nozzle is brutal to it. The exit hole is tiny, a fraction of a millimeter wide, and often fed through a small swirl chamber that spins the stream like water down a drain. Then comes the violence. The instant the liquid exits, the pressure around it collapses to ordinary air pressure. The propellant dissolved in the liquid flashes back into gas, boiling instantly, and shatters the stream into millions of fine droplets. That explosion in miniature is your mist. Here is the elegant part. Every spray bleeds gas and liquid out of the can, so the pressure inside should drop and the spray should weaken, like a balloon going soft. But it does not. As soon as the vapor pocket loses pressure, the standoff is broken, and more liquid propellant boils off to replace what left. The pressure climbs right back to its set point. The can refills its own engine, spray after spray, which is why the last burst feels as strong as the first. So why do some cans ask you to shake them? Because the product and the propellant do not always stay friends. In spray paint, heavy pigment sinks and settles at the bottom of the pool, away from the mixture above. Shaking stirs it back in. That rattle is a small metal ball, called a pea, scraping the pigment off the bottom. Skip the shake, and the can sprays mostly solvent and propellant. Thin, blotchy, wrong. The pressure system still works perfectly. The recipe is what is broken. Run the whole chain one more time. A propellant gas is squeezed until it liquefies and joins the product in the pool. Vapor pressure fills the headspace and holds the can at one steady pressure. Your finger presses the stem, sliding its hole past the gasket and opening the valve. The gas pocket pushes liquid up the dip tube, through the stem, to the nozzle, where flash boiling shatters it into mist. And as pressure drops, more propellant boils off, refilling the engine for the next press. A spray can looks like the simplest object in the house, but inside is a self-regulating pressure engine with one moving part, holding a gas prisoner as a liquid and releasing it, one controlled explosion at a time. Next time you hear that hiss, picture the cutaway, the pool, the pocket, the straw, the standoff. The everyday world is full of machines like this. You just have to slice them open. Thanks for watching The Cutaway.